In this discussion, I want to talk about higher order derivatives, what we might call the standard derivative, the f prime, y prime, dy over dx. That's often called the first derivative of the function f, but a derivative itself is a function and it can have its own derivative. So the derivative of f prime would be the second derivative, and you can denote that by putting an extra accent superscript, and it would be f double prime if you wanted to say it that way. So again, to summarize, the derivative of the derivative is the second derivative. d dx of f prime of x, that means the derivative of the first derivative, is f double prime of x. Similarly, you can take the derivative of the second derivative, and that would be the third derivative, and you can denote that with a third tick mark or third accent symbol, and you could say that as f triple prime. So the derivative of the second derivative is the third derivative. And you can keep going on and on and on and get higher order derivatives beyond the third even. For example, I could ask you to find g triple prime of t for the function g of t equals negative t to the fourth plus 2t cubed plus t plus 4. To do that, you would have to go through finding the first and second derivatives, and you'll eventually end up with the third derivative. So just using the rules you've learned so far, the derivative of g of t, g prime of t, is minus 4t cubed plus 6t squared plus 1. That's the first derivative. Then you take the derivative of the first derivative, and you get minus 12t squared plus 12t. That's the second derivative. And then, of course, the third derivative, which is what you're looking for, would be the derivative of the second derivative. So the third derivative, g triple prime of t, would be negative 24t plus 12. Fairly simple concept. You can take higher order derivatives by continuing to take derivatives of derivatives. I could then ask you to evaluate that at a particular point. So if I wanted to know what the third derivative was when t is equal to 2, I could ask you to find g triple prime of 2. You would simply plug 2 in place of t, and you would end up with negative 36. I've mentioned the first, second, and third derivatives and alluded to the fact that you can have higher order derivatives. Once you get to a certain point, adding more and more of these accent symbols, or what you might call tick marks, gets sort of unwieldy. So at some point, the notation is to change and just put a superscript with the order of the derivative in parentheses. So if you wanted the fourth derivative, you would do y to the power of, and in parentheses, you would put a 4. If you wanted the fifth derivative, it would be y to the power of 5 in parentheses. And in general, the nth derivative would be y to the power of n in parentheses. Simple idea. Higher order derivatives just come from taking derivatives of derivatives, and you can go as far as you like as long as the derivative function you're dealing with remains differentiable. With polynomials, you don't always take derivatives of polynomials, but if you are dealing with polynomials, you'll notice that the degree of the derivative goes down by 1 each time. If you start out with a fourth power, the first derivative will be a third power, the next derivative will be a second power, the next derivative will be a first power, the next derivative will just be a constant, and on and on. Actually, after that, the derivative will be 0. Until you get down to 0, the powers keep going down by 1. If you're taking the derivative of a polynomial function. Another example, find the first 4 derivatives of y equal 1 over x. I hope by now that you've dealt with enough of these problems that you know that when you see 1 over x, you're probably going to want to go ahead and rewrite that as a negative exponent and write that as y equals x to the negative 1, because that lets us use the power rule directly. Once it's in that form, the power rule says take the exponent multiplied by the coefficient, and remember that's an understood 1 there, so it's going to be 1 times minus 1, which is minus 1. And then you take the exponent and decrease it by 1. So minus 1 becomes minus 2. So you could just say that y prime then is the negative of x to the minus 2. Webassign is perfectly happy with that answer. If you want to continue and write that as minus 1 over x squared, that's fine as well. In any case, that's the first derivative. We're looking for the first 4, so we keep going. The second derivative is just the derivative of the derivative. So if you think of this minus as being a minus 1, the power rule says you take the exponent multiplied by the coefficient, so a negative times a negative is going to be positive, so you get positive 2, and then again you reduce the exponent by 1, so minus 2 becomes minus 3. Again, Webassign is perfectly happy with that answer. If you want to rewrite that as 2 over x cubed, that's fine as well. In any case, that's your second derivative. Moving along, the third derivative is a derivative of the derivative. Again, it's power rule, so it'll be negative 3 times 2 is negative 6. Reduce the minus 3 by 1, you get minus 4, so you get minus 6x to the minus 4. Again, you could write that as minus 6 over x to the fourth, but Webassign doesn't force you to. And finally, the fourth derivative. Notice I've switched to my alternate notation because it gets unwieldy to keep adding more and more of these accent symbols or tick marks. The fourth derivative then would be minus 4 times minus 6 is positive 24, and then you subtract 1 from the minus 4, and that would be minus 5. And again, you can write that as 24 over x to the fifth if you like, but you don't have to. That's the fourth derivative. So we've now found the first 4 derivatives of y equal 1 over x. How about this one? If f of x is equal to the quantity 2x squared plus 1 all cubed, find the second derivative evaluated at 2. In other words, find f double prime evaluated at 2. In order to do that, we've got to find the second derivative. In order to find the second derivative, we have to find the first derivative. So the first derivative by the power rule, and again, remember, that's an understood 1, so you multiply the coefficient by the exponent, so you get 3. General power rule says then you write the base down. That's like the u. You write the u down. You decrease the power by 1, making that a minus 2. But then you have to come back and multiply by the derivative of the inside function. The derivative of 2x squared plus 1 is 4x. And you want to clean that up a little bit. You can take the 3 times the 4x and get 12x. So you get 12x times the quantity 2x squared plus 1 squared. That's the first derivative. But remember, we're looking for f double prime, so we've got to take the derivative of the derivative. At this point, you have to notice that the derivative of the first derivative is going to be a product rule. So you've got a function u, which is like the 12x, times a function v, which is the rest of it. Product rule. Remember, the product rule says take first factor times the derivative of the second one, plus the second factor times the derivative of the first. Hope that's second nature by now. So using the product rule, you take the first factor, which is the u, which is 12x. You multiply it by the derivative of the second factor. The second factor is a function to a power, so that's going to be the general power rule. You bring the 2 down front, you write the base down, which is 2x squared plus 1. But then you reduce the power by 1, so the 2 becomes a 1. And finally, you take the derivative of the inside function. The derivative of 2x squared plus 1 is 4x. That's half of the product rule. Now you add the plus sign and you reverse it. You take the second factor, which is the 2x squared plus 1 quantity squared, and multiply it by the derivative of 12x, which is just 12. Now you want to clean that up a little bit. So you can notice you've got a 4x times a 12x, which is, and then times another 2. So 4 times 12 times 2 is 96, and x times x is x squared. That leaves the 2x squared plus 1 just to the first power, and you don't have to write the power of 1. And then on the other side, plus, I would just simply write the 12 first. It's just the standard way to write it. You don't really have to, of course. Now remember, we're going to take the second derivative and evaluate it at 2. So all we have to do now is plug 2 in for every x and do the calculation. So when you plug 2 in to the second derivative, you get this long arithmetic problem, but you have to be careful. You're going to take the 2 and square it, that'll be 4. You're going to take this 2 and square it, which is going to be 4, but then time another 2 is going to be 8. So the 2 squared is the 4 here. The 2 times 4 is the 8 here. Let's see, what else? You've got 2 squared here is 4, but then you multiply it by another 2, you end up with an 8. That's this. The 96 just stays 96. The plus 1 just stays plus 1. The 12 stays a 12. And this plus 1 stays a plus 1. So now you want to work inside the parentheses and multiply any products together. So this 8 and 1 is going to be 9 in both of these places. And then you're going to have to do 96 times 4. When you do all that, you'll get 384 times 9 plus 12 times 81. Remember, this 8 plus 1 here gets squared. And then you've got 384 times 9 plus 12 times 81, and that comes out to be 4,428. A lot of arithmetic, but not difficult. How about this one? It's got a radical in it, so you got to remember how to deal with that. When you have a radical, you want to take a derivative, you're going to write that radical as a fractional exponent. And remember, a square root is a 1/2 power. So that square root of the quantity 6t plus 3 becomes quantity 6t plus 3 raised to the 1/2. Now you can use the general power rule. And again, if you want to think of that as having a 1 out front, you can. The general power rule says you take the exponent times the coefficient, that gives you 1/2. Then you write the base down just like it is, but you subtract 1 from the exponent. 1/2 minus 1 is negative 1/2. So you end up with an exponent of negative 1/2. And finally, by the general power rule, you have to go into the inner function, in this case the base, and take the derivative of the inside. Well, the derivative of 6t plus 3 is just going to be 6. Now it's just a matter of cleaning it up. This 6 can be multiplied by the 1/2, and half of 6 is 3. So you get 3 times the quantity 6t plus 3 to the negative 1/2. WebAssign is perfectly happy with that answer if you were just giving the derivative of the function, but it's actually asking you to evaluate it at a particular point. I've also noticed that I, out of habit, put an x in here, but this is actually f prime of t. In any case, since I'm going to have to continue, I'm going to leave it like that now and take the derivative of the derivative, and that'll give me the second derivative. So the derivative of the first derivative is the second derivative. The derivative of f prime of t is f double prime of t. And now I'm taking the derivative of this. So I take the exponent times the coefficient, that's 3 times minus 1/2, so that gives me negative 3/2, that's here. Then I write the base down, and I subtract 1 from the exponent. So 1/2 minus 1 is, minus 1/2 minus 1 is minus 1/2 minus 2/2. 1 is 2/2. So I get minus 1/2 minus 2/2 is minus 3/2. And then, as always, the final part of the general power rule says to come back and take the derivative of the base, and that would be a 6. At this point, probably a little bit of simplification you can do. You want to multiply the 6 times the minus 3 halves, and notice 6 is like 6 over 1. And you can think of that 2 dividing into that 6 and leaving 3. And so you just end up with a negative 3 times positive 3. So that'll be negative 9 times the base of 6t plus 3 raised to the negative 3 halves power. Now, if I were just calculating f double prime of t, WebAssign would be perfectly happy with that answer. But they actually want me to evaluate it at 1/6. In order to evaluate it, I would feel much better if I got rid of that negative exponent and changed the fractional back to a radical. It just makes it easier to plug in. So my suggestion at this point, if you're going to actually have to evaluate it for a particular value of t, get rid of the negative exponent and the fractional exponent. So that's what I'll do here. So what I do is, I notice that the negative 3 half exponent in the numerator, if I push it down to the denominator, becomes a positive 3 halves power. But I still want to get rid of the fractional exponent 3 halves and change it back to a radical. So the last thing I do before plugging in is remember that the denominator of the fractional exponent is the index of the radical, and when you don't put anything there, that index is an understood 2. You usually don't write it in there, but that's actually an understood 2 when you're doing square roots. And then the numerator of the fractional exponent is the power. So at this point, and again, I need to change that to a t. Out of habit, we use x so much that we get in the habit of writing it. Just plug 1/6 then for t right here and see what happens. So I take that 1/6, plug it into the second derivative, and I plug 1/6 then for t. I get a 1/6 right there, and luckily that comes out fairly nicely because 1/6 of 6 is just 1. And then 1 plus 3 is just 4. And the square root of 4 is 2. And then 2 cubed is 8. The numerator stayed minus 9 the whole time. So there's the second derivative of the original function evaluated at t equal to 1/6. Nothing difficult about it if you've got the basics down. If you know all your derivative rules, can do them without any trouble, the idea of doing higher order, which is simply taking more and more derivatives of derivatives, is not any harder. It may take a little longer, but if you know your formulas, you practice, and you can do these, then it's not any harder than anything you've done before. Let's end with an application. We've already seen from earlier that the velocity of a free-falling object, if you ignore air resistance, is given by the derivative of its position function. In other words, the derivative of the position function, and we're going to use s a lot of the times to stand for the position function. The derivative of the position function is the velocity. So if you start out with some function which tells you the position of an object, in this case, if we're talking about a free-falling object, it would be the height above the ground, or it could be written in terms of how far it's fallen, but most of the time it's height above the ground. You just have to read what the S stands for in a particular problem. In any case, the important thing is the derivative of this position function is the velocity function. We already learned that. Here we're adding another physics fact, and that is if you take the rate of change of the velocity with respect to time, that's the derivative of the velocity, you get the acceleration. In other words, if you start out with a position function f of t, the first derivative is the velocity, the second derivative is the acceleration of the object. Let's apply that. Suppose a ball is thrown upward from the top of a 160-foot cliff as shown. In other words, this person is at the top of the cliff and they're going to throw the ball up, but then gravity is going to catch it, of course, and it'll start falling. So initially it goes up for a bit and then it starts falling. It turns out the position function for this situation here is given by this polynomial negative 16t squared plus 148t plus 160. And we want to find the height, velocity, and acceleration of the ball at t equals 3 seconds. Remember, the position function tells height. So to find the height of the ball, we use the original position function. So I know the answer to the height part is going to come from the position function. But I also want to know the velocity, and I know that the answer for the velocity part of the question is going to come from the derivative of the position function. So the derivative of negative 16t squared is negative 32t. The derivative of 48t is 48. And finally, I know when I want to deal with acceleration, I have to take the second derivative, which is the derivative of the velocity. It's the second derivative of the position function. So the derivative of the derivative of the 48 is just going to be 0, but the derivative of negative 32t is negative 32. So now I can go back and evaluate each of those at t equals 3, and that'll give me the 3 answers they're asking me to find. So first of all, if I plug If I plug 3 into the position function, I'm just going to plug a 3 in here and a 3 in here and do the calculation. I won't bore you with all the details. You'll get 160 feet. So after 3 seconds, the ball is at 160 feet. Not that it really matters, but remember that was a 160-foot cliff, so that means that when that person threw the ball up, after 3 seconds, it had fallen back to the level of that person on the cliff after 3 seconds. It's neither here nor there, but it is interesting that it's a 160-foot cliff, and after 3 seconds, that ball that was thrown upward had gotten back down to the 160-foot height. After 4 seconds, it would be lower, headed toward the ground, of course. The velocity is the first derivative of the position function. So you'd plug t equal 3 into the velocity function. That's negative 32 times 3 plus 48. That comes out to be negative 48, and this is in feet per second. And finally, the acceleration is the derivative of the velocity, which is the second derivative of the position function. And notice it's negative 32. The units happen to be feet per second squared. But it's just 32 because there's no t in there. There's no t in that expression. And because there's no t in the acceleration function, that just means the acceleration is the same all the time. So at 3 seconds, the acceleration is negative 32, but at 4 seconds it is as well, and at 1 second it is. And I say at all times. Well, it's true until it hits the ground. Obviously, after it hits the ground, it's not accelerating anymore. But at all times, up until the point it hits the ground, the acceleration is negative 32. There's really nothing to plug in because there's no t in the expression for acceleration. So you need to practice this. You need to think about the relationship between a function, its derivative, and the derivative, the notation, how it works. Practice your formulas, get them more and more second nature, and then make sure you understand the applications where, in this case, we're talking about velocity and acceleration.